Welcome to Methods in Biostatistics. Today, we are diving into the fascinating world of probability distributions. Imagine trying to predict the unpredictable, like the exact height of a plant or the outcome of a coin flip. While single events might seem like random chaos, looking at many events together reveals beautiful, predictable patterns. By the end of this video, you will understand how we use these mathematical blueprints to turn uncertainty into reliable science. Now that we know we are looking for patterns in chaos, let us define what a probability distribution actually is. Think of it as a complete mathematical map or blueprint. It lists every single event that could possibly happen in an experiment and pairs each event with its exact mathematical chance of occurring. A crucial rule here is that if we add up the probabilities of all these possible outcomes, the total must always equal exactly 1. This total of 1 represents absolute certainty that at least one of the outcomes will happen. Building on that foundation, we can categorize these distributions into two main types based on the data. Discrete distributions count whole numbers, like the number of cells in a sample. You cannot have half a cell. Continuous distributions, on the other hand, measure things that can have infinite decimal places, such as a patient's weight or blood pressure. Understanding both types is the absolute foundation of all medical research. Without them, epidemiologists could not predict disease outbreaks, and we would have no way to set normal reference ranges for healthy blood sugar levels. Let us start with the simplest type of scenario, which brings us to the binomial distribution. Imagine you are testing a new antibiotic. For each patient, the drug either works, which is a success, or it does not work, which is a failure. There is no middle ground. The binomial distribution is perfectly designed for this. It helps us calculate the probability of getting a specific number of successes in a fixed number of trials. The prefix bi literally means 2, reminding us that this distribution applies whenever there are exactly 2 possible outcomes for any given event. This concept translates into a powerful mathematical equation. The binomial formula calculates the probability of getting exactly k successes. Let us break down the symbols. The letter n stands for the total number of trials, like the number of patients. The letter K is the specific number of successes we want to find. The letter P represents the probability of success for any single trial. The term 1 minus P represents the probability of failure. The bracketed n over k is the binomial coefficient, which calculates how many different ways we can arrange those successes. If you increase the probability of success, the distribution naturally shifts to show that higher numbers of successes are much more likely. Before we move on, let us see this formula in action with a concrete example. Suppose a new flu vaccine has a 70% chance of preventing infection. We give this vaccine to 5 different people, and we want to know the probability that exactly 3 of them are protected. We know our probability of success is 0.70, our total trials are 5, and our target successes are 3. We plug these into our formula. The combination term evaluates to 10, meaning there are 10 ways to choose 3 people from 5. We multiply this by the success portion, 0.343, and the failure portion, 0.09. Our final answer is 0.3087. This means there is roughly a 31% chance that exactly 3 people will be protected. Now that we have mastered counting successes in fixed trials, what happens when there is no fixed number of trials? This brings us to the Poisson distribution. Sometimes we need to count how many times an event happens over a specific period of time or within a specific area. Imagine counting rare genetic mutations on a strand of DNA, or the number of patients arriving at an emergency room in a single hour. The Poisson distribution is perfectly designed for these situations. It helps us find the probability of a given number of events occurring, provided those events are rare and happen independently of one another. To calculate these rare events, we use the Poisson formula. Conceptually, this formula relies heavily on the average rate of occurrence. Let us look at the symbols. The Greek letter lambda is the most important part. It represents the average or expected number of events that usually happen in that time frame or area. The letter K is the exact number of events we are trying to observe. The letter E is a mathematical constant, approximately equal to 2.718, which naturally appears in growth and decay processes. The denominator is K factorial. If the average rate lambda increases, the probability of observing a higher number of events naturally increases as well. Let us apply this formula to a real-world microbiology problem. A microbiologist knows a water sample typically contains an average of 2 harmful bacteria per milliliter. What is the probability of finding exact 0 bacteria in a 1 milliliter sample? We use the Poisson distribution because these are rare, independent events in a fixed volume. Our average rate, lambda, is 2, and our target, k, is 0. We plug these into the formula. Any non-zero number to the power of 0 is 1, and 0 factorial is also mathematically defined as 1. This simplifies our calculation immensely, leaving just e raised to the power of -2. The final answer is approximately 0.1353. This tells water safety inspectors there is about a 13.5% chance a sample will be completely free of bacteria, despite the average being 2. We have looked at discrete counts, but what about continuous data? While binomial and Poisson deal with whole numbers, the normal distribution handles continuous measurements. Think about human height, blood pressure, or the weight of apples on a tree. These traits do not fall into neat, separate categories. Instead, they blend continuously. The normal distribution describes how most of these measurements naturally cluster around a middle average. As you move further away from that center, extreme values become increasingly rare. This behavior makes it the most important distribution in all of biostatistics. The mathematical engine behind this continuous clustering is the normal distribution formula. While it looks intimidating, it simply calculates the height of the curve at any given value, x. Let us define the symbols. The Greek letter mu represents the population mean, which dictates exactly where the center of the curve is located. The Greek letter sigma represents the standard deviation, which tells us how wide or fat the curve is. The constants pi and e ensure the total area under the curve equals exactly 1. If you increase the standard deviation sigma, the curve becomes flatter and wider, meaning your biological data is more spread out. Now that we have seen the formula, let us visualize what it actually creates. Here, you are looking at the famous bell curve. The horizontal axis represents the continuous values we are measuring, and the vertical axis shows the probability density. Right in the middle, at the highest peak, is the mean, mu. Notice the dashed lines marking the standard deviations. The shaded blue regions show how data is distributed. 68% of all data falls within 1 standard deviation of the mean, 95% within 2, and 99.7% within 3. This perfect symmetry allows researchers to easily identify outliers and establish confidence intervals for medical tests. The bell curve is an ideal model, but nature is not always perfect. Not all continuous data forms a perfectly symmetrical bell curve. Sometimes the data is pushed to one side. To describe this imperfection, biostatisticians measure skewness. Skewness specifically measures the lack of symmetry in a distribution. If a distribution has a long tail stretching out to the right towards higher numbers, we call it positively skewed. This often happens with biological data, like hospital stay durations, where most people stay a few days, but a few stay for months. Conversely, if the tail stretches to the left, it is negatively skewed. While skewness looks at symmetry, another measurement looks at the peak. This brings us to kurtosis. Kurtosis measures the tailedness, or the sharpness of the peak of the curve. A distribution with a very sharp peak and fat tails has high kurtosis. In practical terms, this means extreme outliers are much more common than a standard normal distribution would predict. On the other hand, a flatter curve has low kurtosis, meaning the data is highly uniform and outliers are rare. Understanding both skewness and kurtosis is crucial because many statistical tests require perfectly normal data to work correctly. We have covered a lot of ground today, so let us summarize the most important ideas. Probability distributions are truly the mathematical language of uncertainty, allowing us to make confident scientific decisions. Remember that the binomial distribution is your tool for counting discrete successes in a fixed number of trials. The Poisson distribution steps in when you need to track rare, independent events over time or space. Finally, the normal distribution is the essential bell curve for measuring continuous biological traits. By mastering these concepts, you now have the foundation to look at any set of biological data and understand the hidden rules governing its behavior. Great job!